Maybe while we wait, just out of curiosity, is there anyone that is attending today's lecture that had not been present yesterday? If you can maybe just type in the chat saying me. Nice. Okay, great. It seems that, oh, one person. Oh, yeah, of course, Ronald, yes. Welcome, Ronald.
There's actually going to be a second person. I spoke with one of my colleagues and she was interested in attending as well, so she got the recording from yesterday. So
okay.
I think she probably already logged in.
Yeah, that's obviously no problem at all. So she's most welcome. And if there's questions, just ask.
Okay.
But so I'm going to start. I'll keep an eye on the waiting room. We're actually starting a little bit easier today than we did yesterday. Yesterday, I told you the beginning of this course is extremely theoretical. It's just definition upon definition upon definition. So today, hopefully, I'll go a little bit lighter on you. And we're actually starting off very simple. So I can tell you all to just sit back and relax and enjoy a 7.5-minute video. That I find is a nice recap of most of the theory that we handled yesterday. So it's just about antennas and electromagnetic radiation in general. So just that we're all on the same page again. Now I'm going to share my screen and hopefully I'll be able to share the sound with you as well. So I hope you can hear the sound. If you can't, please let me know. So you should all be able to see the YouTube video, I hope.
Yes, I can see.
Great. And if I start playing, do you hear the sound?
Modern world, we humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist Heinrich Hertz was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised a question: how do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of 2 circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of the charge has caused an electromagnetic disturbance or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends the velocities should be zero, and in the middle the velocity should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the chargers are far apart and when the velocity is zero. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t by 8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When two charges meet at the central point, the deformed line also meets there. After that, it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now, let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With the continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way. When an alternating current passes through a circuit, it faces opposition from the combined effects of resistance, inductance, and capacitance. This combined effect is known as impedance. According to the maximum power transfer theorem, to transfer the maximum amount of power, the load impedance should match with the source impedance. For further understanding, let's take an example of a circuit containing an alternator as a source and a motor, bulb, etc. as a load. In this setup, to achieve maximum power transfer from alternator to the load, the impedance of the load must match with the impedance of the alternator. A similar impedance balance is required in the case of an antenna system. Since an antenna works on high-frequency signals, the impedance of the transmission lines also becomes important. Hence, to achieve maximum power, the impedance of an antenna should match to the impedance of the source and transmission line as well. If the impedances do not match, some portion of the power would be reflected back to the source instead of radiating outwards from the antenna. A free space has an impedance value of 377 ohms. In a parabolic antenna, a waveguide is used as a transmission line, which has a different impedance value from the free space. That's why a feed horn is also included in a parabolic antenna. This way, the impedance of the waveguide is matched with the impedance of the free space so that the EM waves can be received properly. We hope.
Okay, so I hope you had the sound there, because I'll be honest, I did not get the sound. So, but I didn't see anyone saying there's no sound, so I assume it all went according to plan. Great, thanks for confirming. I'm just opening our slides for today. And again, now I hope you can all see the screen saying fundamental antenna elements. This one I'm moving my cursor on. Correct? Can someone maybe just say something, because I want to make sure that
we can see it.
Yeah, I had a problem with my sound. If I share it through Zoom, I hear nothing, so I've stopped doing that. So
do you want us to keep an eye on the chat?
And if there's something or someone alerts you, and then
yeah, I have it open, but at all times, please, if you notice that I'm ignoring someone or anyone, if you feel ignored, just speak up. Then I have no problem in addressing your question immediately. So please do that. Right, so this recap video, it's actually, when I found it, I noticed that it's about a summary of a 3-hour lecture, and I find it does it really well. I think it's one of the best qualitative explanations for the radiating mechanism of especially wire antennas. So I hope you could follow that, and at least it created an image for you for exactly how these antennas operate. So I hope you'll be able to use that when we start looking at these antennas in a bit more detail, especially from a design point of view. So today we'll be looking at a number of antennas, and for that we'll start with antennas. Up until now we've only looked at antennas when they're in free space. And of course that nearly never happens. It's only when you are placing an antenna on a satellite in space, and then even then it's still not in free space because it's still attached to a satellite. So there's always interaction with the antenna's reference plane or the ground plane. And we'll look at techniques in which we handle that and use that as well. Then zoom into wire antennas. We'll look at the microstrip antenna. I think that's mostly familiar to you as a patch antenna. We'll look at aperture antennas, and these are your horn antennas. So in the end of the video, you saw the reflector antenna with this horn antenna feed, and we'll look at the operating principle of these aperture antennas. And then lastly, we'll look at reflector antennas. And that is a summary of just the antenna elements we'll look at in this course before we move on to antenna arrays, hopefully within today's lecture still. So the video nicely showed again how this operating principle of this half-wave dipole antenna. And I think yesterday we ended almost with this image here, where we said it has to be, as I just said, half a wavelength in length, so that the current distribution is a maximum in the center. So we saw from Maxwell's equations that if we know the current distribution on the antenna, then we can solve the radiated field by the antenna. And that's really the critical part when designing wire antennas, is to ensure that you design your antenna's dimensions to ensure the correct current distribution on the antenna in your frequency range. So you want to have your maxima on the structure at the correct positions to ensure that you radiate your maximum power, or you are the most sensitive from a certain direction. Now, Mohammed, I'm not sure if you are online, but Mohammed asked yesterday about how can you ensure that you get maximum radiation in a certain direction? And that's exactly the art of antenna design.
Yes, I am online. Hello.
Hi, yes. So maybe to show you an illustration of how that can go wrong, or how you have to keep that in mind is, let's have a look at what happens to this half wavelength dipole if you change its electrical length. So with electrical length, I talk about the length of it in terms of wavelength. And you can say that well, you can change the electrical length in two ways. You can either keep the length the same and change the operating frequency. So if we use the antenna at a higher frequency, then it becomes electrically longer. Or you can look at the same frequency and just change the length of the antenna. So in this case, we'll just use an antenna of a fixed length, and we'll just increase the frequency range. And we'll look at what happens to this current distribution on the antenna. And as an effect of that, what happens to the radiated far fields. And I've got a little animation for that I want to show you. It should be on your screen now. So here you can see a half wavelength dipole antenna, the current distribution on the antenna. It shows a polar plot of the radiation pattern and a three-dimensional plot. So we saw yesterday it makes this omnidirectional radiation pattern that is a maximum coinciding to the point where we have the maximum current, or the direction in which we have maximum current. And because we have no current at the end, there's absolutely zero power radiated towards the ends of the dipole antenna. Now let's have a look what happens as the wavelength, as you can see at the top here. If I move this down a bit, you can see it's almost half a wavelength. So now it's nearly half a wavelength, and we still have the maximum in the center, which is exactly why you want to make it a half wavelength dipole. But have a look what happens if we increase the length or the frequency range. So at one wavelength, we notice this is the magnitude, remember, of the current. So technically this current distribution, if you were to look at it in phase wise, not the absolute value, would be a negative on the one side as opposed to the opposite. So you have one wavelength of current when the dipole is one wavelength in length on the antenna element. And you don't really notice the effect yet because electrically these two peaks are still quite close to one another. And this we'll see in the ray analysis that this comes into play. But have a look once it becomes 1.5 wavelength in length. So what you see here is 3 maxima of current on your dipole antenna. And the effect of that is that you have 3 maxima in your radiation pattern. Now, of course, you can understand how this can be non-ideal. If you want to observe a star, for example, or galaxy somewhere in the sky, and this galaxy is located in this point here. If you use this antenna at this specific length, and there's an extremely bright object, let's say the sun, for example, is at this position in the sky, you will receive all the power from the sun at on your detected signal, and it will completely mask the faint galaxy that you want to detect. So this is a really important part when designing antennas is the bandwidth, or let's say the radiation pattern, or the radiated electric field by the antenna really determines the bandwidth. So your antenna can be very well impedance matched for extremely long bandwidth, but then it supports a current distribution that you really don't want in your design or in your application. So it's always the two of these things that you need to take into account. And obviously, as the length of the antenna becomes longer and longer, this entire scenario worsens and worsens. So as we can see, as the length increases, you again see yet another lobe appearing, and this just continues. So we say that the antenna must be half a wavelength in length, and that is only at that frequency. Just keep that in mind. So this was now an antenna in free space. But as I mentioned, antennas are very rarely located in free space. There's always an object around it. And in radio astronomy applications, we typically design our antennas with a ground plane underneath it. And I'll show you the reasons for that now. And aside from that, we have a technique that we can model the ground plane of an antenna, especially if the ground plane is electrically very large. And this is called image theory. I'd say it's not maybe yeah, it's nice to have heard of this before, but. So Stefan asked, what if the dipole is shorter than lambda over 2? That is a very good question. I'll get back to image theory now. I just want to address Stefan's question. The nice thing about that is, and this is exactly what we do with the LOFAR telescope, we use the antenna much lower than lambda over 2's wavelength. But there is a downside to that. Your antenna impedance becomes very capacitive. So it's got a very large reactive component, and that becomes extremely difficult to match to. So you can have a very nice dipole-like radiation pattern for a very large frequency range, but below half a wavelength, your imaginary part of your antenna's impedance becomes almost unmatchable in a sense of power. But in radio astronomy, we can get away with it, especially at the lower frequencies, because the galactic background noise is, or the sky noise is so large that the noise contributed by the electronic front end or the radio front end is, yeah, it's nothing compared to the noise at frequencies below 90 megahertz due to the sky noise. So yeah, in terms of radiation pattern, it's always useful to try and use it below the lambda over 2, but impedance matching, be careful. It can get very tricky. So again, our antenna now in free space, and we want to place it over a ground plane. And that's what's illustrated here. So let me just open, I will see my other to-do lists. There we go. Oh, interesting. I noticed that my my tablet has disconnected. So if you just give me a minute while I connect that, sorry for the technical difficulty this morning. What I'd like to illustrate to you what I mean here is, imagine a ground plane, so an infinitely perfectly conducting sheet of metal. And this is infinite in extent. That is what I mean here with infinite ground plane. And if we were to look at electrical current sources or densities, we can look at two components. We can have a horizontal component or a vertical component. It could be more vertical component. And if you would like to model such a current source over such a large reflecting ground plane, we can apply this concept called image theory. So I want you to imagine this current source that I'm drawing here to be a horizontal dipole, for example, or in this case, a vertical conducting element, conducting electrical current. So to solve this, what we can do is so let's first start with saying that these sources are a distance h above the ground plane. To solve the fields radiated by these sources, we start off by placing image sources. And these image sources we place below the ground plane. And the distance that we place them at is exactly the same distance. So they're mirror sources. So this is again the distance h. There's one difference though. For a horizontally polarized source, the image is exactly the mirror image of that. And for vertical, it's in the same direction. Now, those of you that have done some electromagnetics, you may recall that the electric field on a electric conductor goes to 0. So that's a good way to remember that, is that the field that travels in this direction and in this direction cancels exactly at the plane, so that you have that rule of 0 fields and on the electric conductor. So once you've placed these sources, you've now actually taken into account this reflecting plane. And to solve the fields radiated by these two sources above the plane, you actually solve the fields radiated by all of these sources, so the actual sources as well as the virtual sources. So you actually ignore the fact that there's a ground plane, and you solve all of these in free space. Once you know what the fields are everywhere in free space, you hope that works, yeah. You only use the fields that you've solved in the top half of free space. So everything that you've solved below the ground plane, you ignore and you equate that to 0. Now, I know if you hear this for the first time, you may think, oh, okay, what is he talking about at the moment? But I hope through the next explanations that this will become a little bit more clear to you if I show you how we use this theory called image theory. So as I said, we have two sources, vertical source and a horizontal source over an infinite ground plane. And we can solve the electric field radiated by this in this situation by removing the ground plane, placing our mirror sources, solving the fields everywhere, and then equating the fields below the ground plane to 0. So let's look at this example where we have a dipole antenna. So this is a horizontal current source over a reflecting ground plane. This is exactly the type of setup that we use in a lot of radio astronomy antenna arrays. So LOFA, for example, is a dipole over a ground plane. You'll see later on in today's lecture that I think all antenna arrays are dipoles over ground plane at the moment used in radio astronomy applications. So the way that we can model this then is, first step, we place our image source below the ground plane. So this is at a height of h. We place our mirror image at a distance h below the ground plane. And because it's a horizontal source, you see that the current is mirrored. So it is reversed due to the fact that it's a horizontally polarized source. Can I draw on this? I can. Fantastic. I want you to imagine how this works now at the moment. So we have a current source that induces an electric field polarized in an equivalent manner. If this height here is lambda over 4, a quarter wavelength in length, it means that, well, this is also then likewise a quarter wavelength in length. This vector undergoes a 90 degrees phase shift when it travels upwards. So let's say it rotates inwards into the screen. Then at this point, the vector is actually pointing inwards. Another 90 degrees later, it is aligned the same manner as the original dipole at the top. and it adds constructively to one another. This only happens when this distance is a quarter wavelength in length. For other lengths, it doesn't add as constructively, and for higher lengths, it actually adds very destructively, almost in a similar sense to what we saw now when the dipole length increases. So we can solve the fields radiated by these two dipoles, but we know that we ignore all the fields underneath the ground plane. And what you end up with is this radiation pattern, what we call broadside. So this means that all the power, or the maximum power, is radiated towards, if you look at the dipole or the antenna from the top, so along its broadest dimension, we call this broadside. And you have no power radiated towards the ground plane, which of course is actually, you don't really want that, because in radio astronomy terms, the ground is also noisy. You still detect some, but less power from the ground, and the majority of your signal comes from the sky, where your sources are. So let's look at the other situation. Oh, that was non-ideal. Now, how do I remove my annotations? There we go. If you look at the other one, we've now considered a horizontal, I need a white pen if you can still see. We've considered a horizontal element. Now let's look at a vertical element. So you recall that we said a vertical element the image is exactly the same as the original source, but the polarization of the current is co-aligned. So it's not flipped. I think you all have heard of a monopole antenna, I guess. But for those of you that haven't, this is the description of a monopole. It's literally a conducting ground plane and one wire protruding into the air. So a monopole. So to solve the radiation of this monopole antenna, we can apply image theory. So what I said is you remove the ground plane and you place your image source, as we now have done here. So as you can see, we have no ground plane and our real source and our image source. When the monopole is a quarter wavelength in length, that means our total length of our antenna system that we're analyzing is a half a wavelength in length. And I guess by now you'd be able to immediately recognize this antenna. This is just a half wave dipole. So we can solve the radiation of a monopole by actually just solving the radiation of a half wave dipole, which we now know exactly what that looks like. It's just this nice omnidirectional radiation pattern, the maximum towards the center, and nothing along the axis of the antenna itself. But we've applied image theory here, and to solve the final patterns, we have to ignore all the fields underneath the ground plane and only consider the fields above the ground plane. And this gives you your resulting radiation pattern of a monopole antenna. So this is just in one way a very convenient theory that we apply to solve the radiation patterns of antennas near or adjacent to large reflecting conductors, such as these ground planes. And as in the case of the monopole, it's quite handy to visualize, okay, what is the radiation pattern of the monopole then? I quickly want to go back to yesterday. I don't know if you recall from yesterday that we said for a monopole antenna, or no, for a dipole antenna, I apologize, we have the radiation resistance. Ignore that. For any antenna, the radiation resistance is 2 times the radiated power divided by the current magnitude on it squared. Hope you can recall this. If you compare the total radiated power of a monopole and a dipole, how do you think they relate to one another? Anyone want to take a guess by typing it in the chat? So if I say the total radiated power of a dipole is 1, how much would that be of a monopole, given that you equate half of the fields to 0? Exactly, Diana, exactly that. Yeah, thanks, Piers, Stefan, exactly. It's half that, because the total radiated power, we know we solve from the electric field and the radiation intensity that we integrate over the entire area or the entire volume of the sphere. And since we equated exactly half the power to 0 in the case of a monopole, we have half the radiated power. So I said yesterday that the impedance of a dipole antenna is roughly 73 ohms plus J42. So the impedance of a monopole is, if you have it at resonance, where this term goes to 0, gets you around 30 something. So we can call it 36, but it may be a little bit less depending on the actual length of the monopole. But in essence, the radiation resistance of the monopole is half of that of a dipole. And that comes down to the fact that, you ignore half of the fields. So I showed you that yeah, I see, Peter, I think you're answering Stefan. Okay. Thanks. So we saw now that the half wavelength dipole is actually quite a narrow band response if you ignore the impedance match at the lower end of the frequency band. So I didn't catch that. Could you try again? That's my phone trying to listen to me. So the one way that we can improve the bandwidth in terms of a radiation performance of these wire antennas is by creating a larger antenna structure. So obviously it's not just as simple as just increasing the size in any arbitrary manner, but there's this almost a rule of thumb that says that if you were to enclose an antenna in a sphere, and you look at how much of the area of that sphere is filled by the antenna itself, that gives you a sense of how broadband that antenna would be. So your aim is, if you want to improve the broadband nature of your antenna, or the bandwidth of your antenna, is to fill this sphere with more of your antenna. And this is what we do in dipole antennas or in wire-based antennas. So as you can see, we have this thin wire antenna that we've looked at now as the dipole. But you can increase the bandwidth by going for a biconical nature or structure. And this is by, as the word says, having 2 cones. And the further in the degree to which you extend these cones, filling and utilizing more of your sphere around your antenna, the more bandwidth you can get out of your antenna. We'll look at an example of this in a bit when we look at a bow tie antenna design. So what I mean with a bow tie antenna design, so what you see is a biconical type of antenna element. But as you can imagine, let's say you make these cones, you will probably not do that, but make these cones out of solid aluminum blocks and you mold these out. Then of course you've got quite a heavy structure. What we typically do is we approximate this conical surface using wires, and it almost ends up looking like your typical kitchen whisk almost. But another way, which is quite nice, is you can make a cross-sectional cut of that, and then you only have this bow tie type of structure. As the name suggests, it looks like a bow tie. And this is also to improve the bandwidth as you're using more area. This is not the answer to, let's say, an infinite bandwidth, however. If you look at, this is a biconical antenna element. And what I show here is it's a term called input reflection coefficient that we often use in microwave engineering. And for those of you not too familiar with the term, I'm assuming that not everyone has used this before. What the input reflection coefficient looks at is, let's say you've got a device and you're applying a power to that device's port. So this is our antenna, and we apply a certain amount of power to that port. If you compare the ratio of the power reflected back from that port to the amount that you apply, that is your input reflection coefficient. And typically, you want that to be as low as possible, meaning that most of your power is actually accepted by the antenna and radiated. Very little comes back. But in terms of acceptable amounts, if you're looking at power matching, minus 10 dB is typically said, okay, you've designed a good antenna. And this minus 10 dB then means that 1/10 of the power that you apply to the antenna is actually reflected back, but 90% of your power is actually radiated, or some of it may be lost in the antenna if you have a lossy antenna. Now, what this shows you here is this antenna has an extremely broad bandwidth. This is 30:1. That is enormous. So if your antenna is designed for 1 gigahertz, it operates all the way up to 30 gigahertz, and it still accepts power, and it's all radiated. Or not all, but a lot of it is. But as you see in terms of the radiation pattern, it does change in shape, in distribution as well. And for most applications, especially in terms of bow tie antennas, a 3:1 bandwidth ratio is actually where you're limited to, because once you go larger than 3:1, you either have a narrowing of your beam, or as you can see here in these yellow lines, you start to get these multiple lobes inevitably, like we saw in that initial video that showed that as the antenna becomes electrically larger, you do get these multiple maxima of current on the dipole antenna. So this even still happens when you have a biconical or bow tie antenna, because it's still actually truncated in size. At one stage, you will get these multiple maxima. Just want to read this question from Mohammed. Well, in the dipole antenna, when you see these two directions, I believe you're referring to, for example, this type of representation. Am I correct? So remember, this is just a cross-sectional cut. The entire pattern actually looks, I have to quickly go back a bit. Well, we'll see it now. That's the easiest way to get to it. It's actually a 3-dimensional pattern. Exactly here I have that. So it's an omnidirectional radiation. It's not only in 2 directions, it's actually divided over a much larger angular space. But indeed, it is axisymmetric. So it doesn't matter how you would cut this pattern along which, let's say, if this is our coordinate system here, with X here, and let's say that's Z, and this is Y. It doesn't matter, and we say this is our phi angle here. It doesn't matter along which phi cut plane, so along the ZX or ZY or any of the infinite amount of phi planes we cut this antenna, you will always have this type of polar plot of your radiation pattern, because it's an omnidirectional radiation pattern. It always has a maximum and a minimum in the center. I hope that's clear. Okay, great. So I want us to have a look at some of these antenna designs, and there's a very nice software package. I don't know if you've heard of this, Antenna Makers. It's really a nice, powerful library. If you, there's an infinite, well, not infinite, but there's a very large amount of antennas that you can choose if you want to design an antenna for a certain application. And this Antenna Makers is a fantastic library that you can search and find your most suitable antenna candidates for your application, and also apply an initial design for it without actually solving the entire electromagnetic structure. It actually uses analytical expressions derived for a certain parameter space for each antenna. So you can only tweak a few parameters and it gives you a good estimation of the performance. And this is the software package. This is what it looks like. You can, for example, go to find, and there you can see that you have, waiting for it to load, 372 types of antenna elements that you can look at, search, and potentially design. They give also very good documentation on each antenna type to get you started. So it's really good software, and there is a student version available. So, yes, cost. University licenses are available. It's a subcomponent of CST, which I'll type here. And that is by, oh, well, I typed this correctly, Dassault Systems. I hope I do. Dassault Systems. And I typed it to the wrong person, but there is a student version available. So it's called, as I say here, Antenna Makers. And I would suggest that you try and obtain the student version. It has actually quite a number of nice antenna templates for you to start with, at least to see if this is something for you. But we'll be using it for, as you can see, I've prepared most of the designs for most of our designs that we'll be looking at. So our first one is then a dipole antenna. You have to start somewhere. So let's say we want to design a half wavelength dipole antenna at 1 gigahertz. Who can take a guess at what length that should be? If you don't read it on the screen. So as I say, at the frequency, if not, is 1 gigahertz. What should the length be? Someone says 0.6 meters. Stefan, I would say calculate again. What's our wavelength at 1 gigahertz? Anyone want to take a guess? Wavelength? Yeah, Diana says 0.3 meters. That's correct. That's a wavelength. So, and the dipole should be half a wavelength. So I think Janina said, so lambda is 0.3. Yes, exactly. Lambda over 2. And that gives you around 142, well, 100, actually 150 millimeters. So I asked Antenna Makers to do that, to design an antenna for us. And this is then the design that it made. It's just a wire. And in the middle here, you can see the excitation port here. And if you look at the length, they made it 14.3 centimeters. So 140 143 millimeters. Now you remember yesterday that I mentioned that, or I just mentioned it as well, that the impedance of the dipole is actually slightly inductive. So you have that, we said that Z dipole is equal to 73. Oh, this doesn't write well at all. 73 plus J 42. That must be it. And that the way that we can reduce this to 0 is by shortening the dipole slightly. And you'll see that that's exactly what antenna makers did. It actually reduced it slightly, making it, I think, around 0.48 lambda. Now, what I want to look at is the impedance of this. So we have 1 gigahertz here, and what the solid line here shows is the real impedance, and this dashed line here shows you the imaginary impedance. I hope I can zoom in here. And what you see here is that 1 gigahertz, we actually still have quite a large imaginary component. Our real part is just around 70, but not quite. But yeah, we still have this imaginary component. So antenna makers didn't quite get the design right. It's not yet where it should be. So what can we do to this antenna to make sure that the imaginary part goes to 0 at 1 gigahertz? At the moment, it's more inductive. So the antenna has got a positive reactance. So anyone want to take a guess? What do I do to the design to make sure that the yes, someone says shorten it, Miroslav, exactly. So we shorten the antenna slightly. So antenna makers was not quite right with the initial guess. And then that's exactly what I did here in the next tweak. So I've just changed the length slightly. Sorry, just a second. So I hope you can see this comparison now, if we only look at the graphs. The black curve now is this new design. So what we did is the length had been 143 millimeters, and we've now shortened it to 138 millimeters. So just 5 millimeters shorter. So, and there you can see, if we zoom into this part here, at 1 gigahertz, we're at 5 ohms. We're very close to 0. And that's exactly what we wanted to achieve with this design, by just shortening it slightly. I want to show you what's the effect of this on the input reflection coefficient. So we said that you want to see how much power is now reflected back if you were to apply a power to this antenna element. When we do this, we assume the following. So the reflection coefficient. The source impedance, in this case, is 73 ohms. So we said that the dipole impedance has an antenna impedance of 73 ohms. And now we're assuming that the source we apply to it is also 73 ohms. So exactly like that video showed the alternator and the motor connected to things. We're now making sure that both of their impedances are the same if the reactance is 0, if the imaginary part goes to 0. So here you can see this antenna is very well matched now. Initially, the blue design that was too long missed 1 gigahertz. So you can see it didn't really have the best matching. But once you shorten it, then you get this minus 30. So 1/1000th of the power reflects back, actually. So you've got a very efficient antenna in this case. So next, let's look at the radiation patterns. One thing I want you to notice here is they show you here the far field versus angle. So this is a polar plot. And you notice the term here, E-plane. I think you remember yesterday I mentioned these various planes that they talk about, E-plane and H-plane. So this should already give you an indication visually of where this far field cut had been taken in the three-dimensional pattern. And in the case of the E-plane, they've taken it in a plane that contains the electric field vector. So if we look at our model, this is our dipole antenna, and we know that the electric field, well, we saw in the video, if you get a plus here and a minus here, the electric field extends across like this. So any plane containing this vector is the E-plane. So you can imagine a cut plane directly into the screen here almost, and this is what is shown. In the E-plane plot like this. Another thing I want you to notice here is this was the first antenna design that had been designed, and then we shortened the design. So you see in terms of radiation pattern, there's really no difference. It's only in terms of impedance that you've actually changed the performance of the antenna, which is a good thing in this case, but it is a very small, change. And then of course we can look at the three-dimensional radiation pattern. And here we see that omnidirectional pattern. So Mohammed, when you asked again if the maxima is only in two directions, I think you can see here that as you rotate this radiation pattern, it's actually only a minima. This is then where the dipole is positioned. As I've rotated it now, the dipole would be positioned along this axis here. And you have a maxima all around in this omnidirectional radiation pattern. The one thing that is, well, so Diana asks something when you're designing something in HFSS, so that's another electromagnetic simulation software. And HFSS is truly that. It's a discretization of Maxwell's equations, and it really solves electromagnetically as the waves as they propagate through space. So no, you should not be worried about your job, Diana. It's a good thing. So it's a really handy tool, but you will never take an antenna maker's design and run it. You always see this model here, model export. And this gives you the option to export your model to a full wave simulator. And that's exactly where you do your design. This just helps you to select the best antenna for your job. And of course, from an education point of view, yeah, PTS is not very reliable. It's nice to show you an indication. So we mentioned the antenna's performance is characterized in two things. The one is the antenna impedance, and the other is the bandwidth. The antenna impedance is the bandwidth. The other one is the radiation pattern. And if we just look at what happens to the bandwidth of our initial design, so our initial design, we achieve a minus 10 dB level bandwidth of around 8%. Then we shortened the design and it became a little bit larger. Oh, I'm looking at the wrong one. My bad. Sorry, that was I clicked on the wrong place, so I was confused by that myself for a moment. We shortened it, but it didn't change really. So we didn't change the thickness of the dipole at all, and nothing happened with the antenna's bandwidth, only the frequency in which it was matched. So to be able to increase the bandwidth of this antenna, I kind of just said it, but what do you think we have to change? If someone wants to type it in the chat. So which dimension can we change to make it more broadband? Anyone want to take a guess? So we said that to improve the bandwidth of an antenna, you should fill, if you were to draw a sphere around the antenna, you should fill the antenna or the sphere with more of the antenna. So yeah, Miroslav mentions the diameter. And that's exactly what I do in the next tweak is I change the diameter. So at the moment it is 30 micrometers, extremely thin. I don't make it much broader, but I change it to, well, 10 times as broad, 300 micrometers. So initially the bandwidth was 8.8 or 8.87, and you can see the bandwidth increases to around 10%. Not significant, but we also didn't really fill a lot of the sphere. We only made it, instead of 30 micrometers, we made it 300 micrometers. So there are ways to increase the bandwidth even more. And that is, of course, by using something like the bow tie antenna. And I think like all good software demonstrations, it will now crash on me. No, we have it. Good luck today. So as I said, to increase the bandwidth, we can either make a biconical antenna, so having these two conical structures as the dipole instead of the two cylinders. But a convenient way that we often use this is just to do this in terms of to print it on printed circuit board. And then you get this resulting bow tie antenna. You don't necessarily have to print it, of course. You can also use metal plates. But in this case, it's got, just to show you the sketches here, you have this substrate with a certain dielectric constant, relative permittivity, and then the structure, which is this, the bow tie, the metallizations, these two triangles. So again, we designed this antenna, or I just went for a random design. I said, okay, we want a minimum frequency range of 800 megahertz. Now, you would be quick to think, okay, so I should now make the length of my antenna equal to 800 megahertz, or half at least, half wavelength at 800 megahertz. With a bow tie, it's not as simple to say, okay, that is, it's a good initial guess. But yeah, I would say if you start from scratch, that's a good initial guess, to take your lowest frequency and design this outer length of your antenna as half a wavelength of your lowest operating frequency. In practice, it will always be quite smaller than that because you have got this additional side length as well and more surface for your area for your current to propagate on. So it's a good design step, but ultimately it becomes a barometer sweep to get exactly the frequency band that you want to achieve. So if you look at what Antenna Makers did to solve this performance, 800 megahertz, you see it makes a length here of around 8 centimeters, but that's only one of the petals. So it's actually in total 160 millimeters long. And it's got a separation distance in the middle here for the feed of 2.5 millimeters. Now, if you were to calculate that, you'll see that this length is then actually half a wavelength at around 930 megahertz. So I'll just look at the reflection coefficient for this antenna then. So we said we wanted it from 800 megahertz, and you can see the 10 dB bandwidth is not quite from the 800 megahertz as specified, but it does start around 900. So that's actually where the antenna is half a wavelength in length. Bandwidth-wise, you see you have a bandwidth of 64%. So in comparison with the 10% that we just achieved to the cylindrical dipole, you can see you get a significant improvement in impedance bandwidth. But now let's look at the radiation patterns. So there's two curves shown in the radiation pattern here. The one is this dash curve, and it shows you this is in the phi cut plane of 90 degrees. And the other one is in the phi cut plane of 0 degrees. So if we look at our model preview here, I want you to notice that phi is again defined from the x-axis. So for phi 90, that means that the cut plane is along the axis of the dipole, meaning that you have a 0 along the axis and the two maxima radiated, well, actually, you can say towards the broader sides of the dipole, but it's actually again an omnidirectional radiation pattern, as you can see in this image here. And obviously in the phi naught plane, that's just along this omnidirectional pattern. So you see just a maximum gain on all directions. What's more important is, as we mentioned, that at one stage, at one frequency, some frequencies, your dipole will become electrically too large. And this is what you see back in the pattern. So here we are at 800 megahertz. This is 1.5 times 800 megahertz, 1600 megahertz. You still have your nice dipole-like behavior, but at 2.5 times the bandwidth or the lowest frequency, here you start seeing that the pattern is deforming. And once you get to 3 times, you actually start seeing that you get these multiple maxima, as we saw in the initial video. So even though you can achieve a nice broad impedance bandwidth, the patterns deform. And in terms of the 3-dimensional patterns, hope I can show this one to you. This is then ultimately what it looks like. So you see these multiple lobes forming instead of just the one main lobe. This should be quick for you to answer. To improve the impedance matching then towards a lower frequency, I think you know by now what to do to be able to change that. Anyone want to write it down or write it in the chat? What do I change to make sure that it's better matched? What's a good first attempt to improve the matching in the lower frequency band? Anyone want to take a guess? Yes, exactly that. So you want to make it slightly larger. So it was 79, and we've changed this now to 93. And you can see that, okay, our matching is slightly better at the lower end of the frequency band. In terms of bandwidth, it has shifted slightly, but this is starting to get into the range of, yeah, I would not take this for granted that this is the final bandwidth that you achieve. But yeah, indeed, increasing the size of the antenna element gets you to improve the matching at the lower end. Here it can come at a little bit of a price. So remember that what the pattern was like at 3 times Fmin, so at 2.4 gigahertz. Let's have a look at how the patterns now compare. So the blue curve here was the previous design that was slightly shorter. And already you saw some deformation. But now increasing the length of your antenna has made the antenna even longer, electrically speaking, at 2.4 gigahertz. And you see a much larger deviation in your radiation patterns. So that's the crux of antenna design. You can always win something at the one end of your frequency band, but at the other end of your frequency band, you will probably pay the price for it. This is nicely illustrated in this example. And also why the bandwidth is then limited to at most 3:1 for a bow tie antenna element. Now, again, we started just like the theory I discussed earlier, with an antenna in free space. So there's no ground plane near this antenna, but typically there's always a ground plane, or in radio astronomy terms, especially a ground plane underneath the dipole to make sure it doesn't radiate the power in all directions. So the next design we'll look at is such an antenna design. Right, so this is the half-wave dipole over a ground plane. So who quickly wants to calculate how high above the ground plane should this dipole antenna be? So this distance is RD. What should that be if we want to design again? Diana, I'll get to your question now. So let's say F naught is again 1 gigahertz. What do you say is the height that this dipole should be above the ground plane? While you look at that, Diana, yeah, someone says 0.75 centimeters. Yeah, that's a quarter wavelength, so exactly that. And Diana, to get your question about the actual ratio, I'm not sure if Antenna Magus gives you the output as actual ratio. What it does give you is the co and cross polar field components. So you may be able to deduce that from that, but I'll have to look at it. I can take a look and get back to you on that one. I've not analyzed circularly polarized antennas in Antenna Magus yet myself, so I cannot comment on that safely. But yes, 75 millimeters, that's exactly the height that this should be. And if you look at what Antenna Magus derived, well, it said 70, but pay attention that the distance is taken from the lower end of the dipole, and this thickness is actually quite thick. It's 8.5 millimeters. So that takes you close to the 75 millimeters that this antenna should be above the ground plane. Now, as I said, in terms of the radiation pattern, we see that now we don't have the case that power is radiated towards, well, both sides of this polar graph, but instead where the ground plane is located, we have a significant reduction in radiation. Now, in the image theory examples that I showed you, we showed that there's no power underneath the ground plane. But of course, in practice, you cannot make an infinite ground plane. So you always have this finite ground plane effects where power is still radiated below the ground plane, as you can see here, but at a significantly lower level than your main radiation. If you look at that in 3 dimensions, this is then what we would refer to as, you'll find this in papers as well, a description of a dipole over ground radiation pattern. And this is your typical dipole over ground radiation pattern that you then get maximum towards the broad side and then this 0 towards yeah, towards the backside of the antenna. One thing to also maybe notice, that's if you're interested in that, there's always a difference in the two planes. So the pattern for a dipole, just a horizontal dipole, is always a elliptical shape. So you have that it is more broad in the one plane, let's say in the H plane, than in the E plane, for example. And this is what you see back here, is that the E plane radiation pattern is quite narrow and the H plane is extremely broad, which is fantastic because especially as a radio telescope, you want to detect. But remember, the 3 dB beam width of your antenna determines ultimately where your best scan range is for your antenna array. So if you can have a really broad half power beam width, then you have, you can cover a lot of the sky quite efficiently. I'm going to suggest that we take a 5-minute break, and then I'm going to continue with how exactly we feed such an antenna element. Because now we've just said that, you excite the antenna, but how do we achieve this in practice? So after, say, let's make it a 7-minute break. So at 25 past, we meet one another again. Okay, so I suggest we continue. As I said, we'll now take a look at exactly how do you get a signal onto this dipole, which is also a very crucial part of antenna engineering. You often see that this can take up quite a lot of time to actually realize an antenna design that you can excite or connect something to much longer than you usually expect it to. But in the case of the dipole over ground, this can be achieved rather simply. And the device that we use to achieve this is called a balun. So just to give you a sense of what we are trying to achieve here. Here we want to achieve a differential excitation or a balanced excitation, meaning that we have, I'm going to use a different format for this. This one, here we go. So this is exactly that same image that we just saw. You must just imagine the dipole extending outward here. And what we want to achieve is a balanced excitation at this feed point of the dipole. So meaning we want the one arm to be excited out of phase with respect to the other arm. And this device is called a balun. So if you were to imagine two transmission lines, some device, and at the output you've got one output with reference to ground. So on this side, this is called an unbalanced transmission line. And on this side, we have plus and minus with reference to one another. It's called balanced. And this device converting unbalanced to balanced is called a balun. So that's what we want to achieve to excite our dipole antenna element. And the way that we do this is, you notice that the transmission lines, well, there's two transmission line sections. On the one side, you have the dipole arm extending downwards, and it's actually connected to the ground plane. On the other side, we've got this coaxial port, and I want you to imagine on the inside of this dipole arm, the coaxial transmission line is embedded. So for those of you that never worked with a coaxial transmission line, what this actually is, so as the word says, it's a coaxial transmission line. What this is a cylindrical transmission line with an outer conductor that is connected to ground. So this outer shield here is connected to the ground plane. And you have an inner conductor that carries your reference signal. And if you were to look at the field distribution, then you have this radial type of field distribution if you take a cross-sectional cut of this coaxial transmission line. So this part you see here is actually one of these transmission lines if you were to rotate this image 90 degrees into the screen. And what you have here is this unbalanced side. So what you see is a conductor carrying your signal and a reference that's reference to ground. So this is our unbalanced connection. And this is typically the interface if you were to measure this antenna in the lab. You want to connect a connector to this antenna. And this is where you'll be interfacing with it. But now, of course, we want to get to an unbalanced excitation, or to a balanced excitation, sorry. And what you can notice here is that this dipole arm on this side containing the port, along the entire arm is connected to the outer shield of the coaxial cable. But at the top, this inner conductor is connected to the entire opposite arm. So it's only the signal carrying conductor that carries the signal over to the opposite arm. So if you were to look at the current here, you will have the current on the inner conductor, and of course the return current flowing on the outer conductor. Equivalent, you'll have the current on the inner conductor here, and similarly the current on the inner conductor. And on the opposite side, pay attention to the direction here. The return current is oppositely directed, but on the dipole arm itself, it's actually directed in the same direction as the current on the opposing arm. Now the question here is, why does the current not flow down this side of the conductor? And that's the whole point with connecting this arm to the ground plane, is to ensure that no current flows downwards, but all the current is forced onto the dipole arm. And that's the main intention of this valence structure. And this you can achieve if this height, which it luckily is a quarter wavelength in length. So let's just quickly look at that. If you were to imagine along this line here, it should not have gone like that. For all practical purposes, that should be a straight line. No, it doesn't want to do that. It's a straight line. So I want you to imagine, or not imagine, if you can tell me, this conductor at this point here is connected to ground. So it's actually a short circuit. And if we are now to draw the voltage and the current along this transmission line, just in terms of magnitude, what would the voltage be at this point here, where it is physically connected to ground? Anyone want to take a guess? Yes, Stefan says it's 0. It's exactly that. So our voltage at this point here, so if I were to, I'm going to write voltage in red, and let's make current in green. So the voltage at this point is indeed 0. Now we know that we then get a standing wave ratio, and this standing wave is then a maximum at a quarter wavelength towards the back. So at this point here, we have a maximum voltage. Let's look at the current. The current we know again at a short circuit is the maximum. And this reduces down to a 0 a quarter wavelength away. If we then look at the impedance at this point, we know that the impedance is equal to voltage divided by the current. And we know we have a short circuit, so we have to have 0 ohm at this point here. When we move a quarter wavelength up, and we then look at the impedance, we're actually dividing by 0. So this approaches infinite. So the idea with connecting this dipole section to ground, a quarter wavelength from the height of the dipole, ensures that the current sees an infinite impedance at that point. And current will follow the path of the least resistance. So very little current will flow down the arm, and you'll have a near perfectly balanced feed system at the top here. Now you could always ask, okay, but why not just not connect it at all and keep it open completely? Because that's also just an open. But remember, if you were to just, let's say, cut this arm off here and ignore this entire section, there's always some kind of capacitance back. And at higher frequencies, this effect will come into play a lot more. A short circuit is a short circuit, always. You physically connected it. So electrically, it's much more stable to create a high impedance through a short circuit transformation than by allowing stray capacitance to come into the way of your excitation. So, of course, this all depends on this lambda over 4. And creating broadband valence, I'm going to say, is a topic for another course. So we're not going to go into that here, but it's a good point if you can already start understand this form of excitation. And that's exactly what we just explained, the Balin, how that works. This is another representation of this. You'll receive this in the notes that I sent to you. So we can also look at the monopole. So how would you excite the monopole antenna, for example? So as I said, the monopole antenna is a wire rod sticking above a ground plane that is a quarter wavelength in length. And yeah, here you have again the coaxial cable, as you can see. So to excite this antenna, it's actually rather simple. We've now seen what the coaxial field distribution is, and we said that it is extending radially outwards. I think I see someone in the participant list. Okay, the back. So it extends radially outwards here from the center conductor towards the ground shield. And it's really as simple as that to excite a monopole antenna. You just connect the antenna to the center conductor. And from this point on, the fields radiate towards the ground plane. You have the opposite end here. Here you have an open circuit at the top, transformed to a short circuit at the point where you interface with the antenna. So the current actually sees a very low impedance at this point and wants to run up the monopole. So yeah, in practice, it's quite simple to realize one of these. Let's quickly have a look at the radiation pattern of a monopole. We saw that it's very similar to a dipole, only you ignore half of the radiated far fields. But of course, then if you have a finite ground plane, you can imagine what will happen. As in this example here, we see at 1 gigahertz high, 1 gigahertz, the operating frequency range. The height must be quarter wavelength, so 75 millimeters. Similarly to the dipole, we said the dipole should be slightly shorter than that of a half wavelength. So the same applies here. To get it resonant, we want it slightly shorter than a quarter wavelength. And then, as you can see, it's nearly perfectly matched at 1 gigahertz for this length. Important thing to notice is the impedance, 36.5 and not the 73. So as we said in the beginning, that the radiation power, total power radiated by a monopole is half of that of a dipole. So hence the radiation resistance is also half of that of the dipole. And as you can see back here, instead of the 73, you have 36.5 ohms. And in terms of the radiation pattern, the monopole antenna in this case is of course also located along this axis here, and the power radiates axisymmetrically around the axis. And you have a reduction in the gain where the ground plane is. So towards in the back lobes, you have much less gain than towards the horizon. Not towards the horizon, but towards the upper half of the sphere. Visualized in 3 dimensions, this is then the type of radiation pattern that you get. Very typical monopole over a finite ground plane. Bandwidth-wise, we see again only 10%. So this is similar to the dipole. It's only a cylindrical structure, so you cannot get really a lot more out of the dipole antenna, unless out of the monopole antenna. Exactly similar to the dipole. So Joe asked, what's the effect of replacing the finite conducting ground plane with the Earth sea for that matter? That becomes very tricky. This is not an easy matter. So the first question you must ask is, what is the electrical properties of the sea or the Earth on that specific day? And I say that at the specific day because it also changes, and these changes will reflect back in your radiation pattern of your antenna. So the best bet is to place a metal structure underneath your antenna, because this we can at least to a much better extent model more accurately, especially if you're using a system as a radio telescope. You want to be able to de-embed your beam pattern accurately. And the best way to do that is to simulate them accurately. And if you have soil around and seawater, then yeah, a lot of work would have to go into characterize that very accurately, or at least to take that into account in your simulations to see how much this will influence your beam patterns. So it can be significant. That's what I to answer that question, Joe. To get to a broadband monopole, then, yeah, you guessed it. It's just extending from image theory. We know we can use a biconical broadband dipole antenna, so we can just cut the half off it, and you've got a conical monopole antenna, and then you get the broadband nature. So it's again, to get this tweaked to your correct frequencies, there are some design rules here. They say in this instance, for example, the side length of your conical structure should be 0.28 times the lowest frequency range. But yeah, you can take that as a quarter wavelength as well, and this will get you in the neighborhood. And in terms of impedance match for such a conical structure, it's again an enormous bandwidth that you have here. They only simulated it. We started at 800 megahertz. And they stopped the simulation at 8 gigahertz, and it will just go on most probably because of the nice conical structure, depending on the distance above the ground plane at the end. But yeah, you've guessed it, similar to the bow tie antenna, you are really limited in your bandwidth here due to the deformation in the radiation pattern. So at 800 megahertz, we have a nice monopole radiation pattern, and at around, well, they show it here for 5 times. At 4 gigahertz, you start to see these multiple lobes again, which of course will be non-ideal since you want to steer your beam in one particular direction. Or let's say you want to be sure that your sources are from a particular direction and not from multiple directions. So that's about a summary of wire antennas. And we'll next now be moving on to the microstrip patch antenna, which is It's not really a solution for radio astronomy applications, but in wireless communications, it is used a lot. Yeah, most particularly, I think the Wi-Fi patch antennas, and that we all use all the time. So it's still nice to just go through the theory of this. And it's also, if you ever feel like making a quick antenna in your lab, a nice one to attempt yourself. But before we get to that, just for those of you that have not really worked with microstrip transmission lines before, I'd just like to give you a bit of an overview of that, to give you a sense of, okay, exactly how does this antenna operate? So for a microstrip antenna, what you need is a piece of substrate, so a PC board, and this has a particular dielectric constant or relative permittivity. And the microstrip is realized by having a etched ground plane underneath the substrate and a piece of conductor on the top plane of the substrate. And if we were to apply a signal to the top piece of conductor with reference to this ground plane on the bottom, we have an electric field distribution that can be shown like this. So the electric fields are contained within the substrate, but not only that, they also fringe outwards towards the ground plane. And this is in essence what a microstrip antenna, or what a microstrip transmission line, or how a microstrip transmission line can be represented. The one thing to remember here is we have a relative dielectric constant or relative permittivity. And the effect of this is, so here we have free space, there we have the free space permittivity, and we also have that lambda naught is equal to C naught divided by the operating frequency. Within the substrate, things change a little bit, and it changes primarily in terms of the wavelength, where we have a guided wavelength equal to lambda naught divided by square root of epsilon r. And that's one of the major things to take into account here, is that when you design a microstrip antenna, your wavelengths are now no more just the free space wavelength, but you need to take into account the electrical permittivity of your substrate. Of course, you can get away with that and just float a patch above a ground plane in free space, and then you're back at the same thing again, which some people actually do, and we can get on to why in a little bit. But let's look at the actual patch itself. So for that, I'm turning this substrate 90 degrees, and we're looking at it from the top. So I want you to imagine make it one color, a piece of microstrip transmission line extending outwards, and then reaching a patch antenna. So this patch antenna is just open-ended on the one side. It's not connected to anything. And obviously underneath this entire structure at the back, we have a ground plane. So you should imagine all the way at the back here, on the lower side, it is etched in copper. And the substrate, of course, in between. Now there's some very handy design formulas for, or just to get you started, for example, on the width of the microstrip line. So what this, no, I apologize, that is the length of the microstrip line. And of course, this is the width of the microstrip line. And in addition to that, you have this height of the substrate. And all of these are defined in terms of this guided wavelength. In the notes that I'll share with you, there's some formulas for what the width should be and what the height should be. But what I wanted to focus on now is only this length. So this length should ideally be equal to the guided wavelength divided by 2. And the reason for that, I want to again turn this substrate on its side. Now we're again looking along the side of this, and we have our ground plane underneath. And at the top, we have our piece of microstrip line. And of course, the patch antenna itself. Now, if we were to look at the electric field lines below the microstrip line, as we saw on the top image, this extends just downwards towards the ground plane. If this length is guided wavelength divided by 2, we notice the following distribution underneath the microstrip. So you see that the wave, the standing wave underneath the microstrip is determined by the guided wavelength, not the free space wavelength. And at the edges, similar to what we had for just the microstrip line, where you had these fringing fields extending out of the substrate in free space and then curving back down, you have exactly the same thing here at the edges of the microstrip, where these fields actually extend downward. So they curve into free space and then downwards again. And similarly on this side, you have the same thing happening. So seen from the side here, you actually have these fringing fields. And pay attention to the direction of the fields here. So this is out of the substrate. And very nicely that they're out of the substrate in this manner, especially at lambda, the guided wavelength over 2. These two then are directed in exactly the same direction. So what you actually have when you have a patch antenna are 2 slots that radiate. So you have a slot on the one side radiating and a slot on the opposite side radiating. And these slots are half a wavelength apart. And because they are half a wavelength apart, the electric fields are copolarized and co-aligned, and they actually add in phase towards broadside, so away from the antenna element. And this you only achieve when this is lambda g over 2, while you achieve it optimally. So if we have to have a look at the radiation patterns for that, you see that you actually have these 2 slots that add collectively and radiate towards broadside. You get a really nice and broad beam pattern out of this. So half power beam widths, well, 60 to 80 degrees. The only thing with that is bandwidth again. So we have this wavelength dependency. And yeah, if you have a substrate with a high dielectric constant, then and a very narrow substrate, so your height is very small, then you'll see that you can get a very narrow bandwidth from this design. If you want to increase the bandwidth, you need to allow your fields to be more loosely bounded along the edges, so less confined within the substrate, and yeah, in a sense, easier for the fields to escape from the slots. So that would mean going for a lower dielectric constant in your substrate, or increasing the height up to a certain point, of course. And these are the typical design guidelines that show you how to achieve an increased bandwidth for the patch antenna. As I illustrate here in this design, you can actually achieve a dual polarized design as well by having a square patch. So you excite it from the one side, and you have your fringing fields, and you can excite it from the opposite side, and similarly. So you have the same patch antenna as a dual polarized design. Now, I hope you can still all access Mentimeter. So I'm going to share, let me do it like this. You should now all see this again. If you all go on your cell phones to menti.com and enter that code again, I have a few questions for you to have a look at. Everyone logged on, okay? I see some answers coming through, nice. For those of you that need the code again, it's menti.com, and the code you enter is 1440125. Just posted it in the chat. I've got 9 answers so far, 10, there we go, all coming in. I've got 11, I'll wait till about 15 and then I'll show the results. 12. 14, one more, 15, there we go. I think the rest are anxiously waiting for the answer. So you're very much divided in this. Let's quickly have a look at the question. It says total radiated power of a quarter wavelength monopole of an infinite ground plane is PM. What is the power rated by a half wave dipole? So yeah, you have a monopole radiating some power, and you know that the dipole radiates exactly twice the amount of power than a monopole antenna. So remember the monopole antenna, you have half the fields cancelled from the dipole, so you actually have half the power gone. If we quickly have a look again at this slide. Yeah, you see that for a dipole, you have a perfect omnidirectional pattern, but for the monopole, half the power is gone. So in the sense of a dipole, you have twice the radiated power. So indeed, twice the radiated power, if you got that, nice. One more, well, a few more coming up. I hope you can all see the image in this question. Someone showing it, yes? Okay, so I guess most of you, seems that most of you got this, some of you, but indeed the purple line is the broader one. I know it's quite close to see to one another. Maybe the colors are also quite similar to one another. So apologies if they weren't actually that easy to discern between one another. But indeed, the purple is the thicker, because if you remember from antenna megas, if you go back to our dipole antenna, the broader bandwidth of 10% was for 30 micrometers and of 300 micrometers. And if you look at the design for 30 micrometers, then you see it's a slightly narrower bandwidth. So indeed, purple was the correct answer. So one more coming up. Okay, so some more participants. Nice, welcome, thank you. Right, so the question was, which one is the H-plane? And yeah, so the H-plane is the plane containing the magnetic field vector as well as the direction of maximum propagation. So I think, as you're all aware, the current at this stage at the feed point flows along this direction. If I annotate it here, our current flows in this direction, and the magnetic field lines rotate around it. So in this case, with the current flowing along the y-axis, we have the magnetic field contained in the on the xz plane. So indeed, if you had said, it should be there, the xz plane, you were indeed correct. It is in the xz plane. Next one. So for this one, you will have a few minutes. Now, if I recall correctly, I am asking you to design a patch antenna. So you will need a few formulas. I will put it on the screen again where I just wrote it. Mostly the formulas I think that you will need are on your screen now. So have a look at this and see if you can design this patch antenna. I gave you 4 minutes. and you can round your answer to the closest integer, so no decimal points. Oh, I see I accidentally ended this a little bit too early. Apologize for that. Don't know how that happened. So that went a little bit too fast. I'll try and figure out how that happened. So make sure that doesn't happen for the next question again. But I see we have 134. So let's quickly have a look at that. Because 34 is indeed the correct answer. First of all, what we want to calculate is lambda naught. So that is just 300 divided by 2400 for the operating frequency. And once you have lambda naught, you want to compute the guided wavelength. And that is then again just lambda naught divided by the square root of the dielectric constant, which was 3.38. Then you get your guided wavelength. And if you divide that by 2, you get your length equal to 34 millimeters. So yeah, have a look if you can get to that again. But let's see what Antenna Omega said. I see chat. Yeah, sorry about that, Stefan. There was a slip up on my side. I moved the window and then suddenly the timer stopped. So note to myself, don't move the window. So if you got 34, well done. The next time I'll keep the window where it is. Just want to open the correct design. Here we go. So we asked antenna megas for 2.4 gigahertz for a substrate thickness of 1.524, as I had in the question, and a relative permittivity of 3.38. And let's see, the length, it actually got it as 33.02 millimeters. So just by this quick 2-minute calculation, you can get to, well, almost your final design if you were to go for a square patch antenna. But let's look at the achieved frequency range here, or the achieved input reflection coefficient. So we asked for 2.4 gigahertz, this green line, but we see that we've actually missed the mark completely with this length. Well, not completely, but given that it's such a narrow bandwidth design, the band is not even 1% in bandwidth, you can really just a small perturbation and then you're completely mismatched. As you can see here, you've got a reflection coefficient of less than 1 dB. So this is extremely mismatched. So yeah, you can guess it. What do I do to get this antenna now matched to the right frequency? Anyone want to quickly type that in the chat? There's one thing that you can do. What happens to the length? Shorten or increase? Decrease L, yes, Diana, thanks. And that's exactly what I did here. I changed the length to 31 millimeters and it's matched to 2.4. Now, okay, you may ask, right, we have this design formula that says the guided wavelength must be or the length must be the guided wavelength divided by 2, and then you're not actually quite there yet. So why is that? And for that, I want to go back to this very rough sketch that I made of what the fields look like. The entire operating principle of the patch antenna is on these fringing fields that extend on the side to create these radiating slots. This also has another effect, and that is if you were to consider the length, it's not actually the edge of the slot, but the length of the antenna also takes the fringing fields into account. So the length doesn't necessarily start here exactly at the edges of the antenna, given the fact that the fields fringe out from the sides of the patch. This results in an additional electrical length that you need to take into consideration. So the guided wavelength underneath the patch is good to get you started, but in practice, you will always have it slightly lower. And that in a nutshell, literally, is patch antenna designs. With that, I think you can at least, you should be able to, at home even, take any square metal piece and design a patch antenna for a Wi-Fi frequency band. And before we continue with aperture antennas, I suggest we take another short break. Let's meet again at 20 past. Okay, let's continue again. Last section for today. And this is aperture antennas. So we're moving towards horn antennas and reflector antennas. Yeah, well, the horn antenna is probably, I think, one of the most widely used, although that should be careful now because I think patches are certainly catching up. But in terms of illuminating reflector antennas, that is one of your standard options. And there's various variations on these two fundamental types, the pyramidal horn antenna and the conical horn antenna. So my intention with this section is just to give you a sense of, okay, how do these antennas operate as opposed to the patch and the wire antennas? So I hope after having seen this next section, you'd be able to at least look at a horn antenna and think, okay, I can actually see what the fields in this aperture should be or could be like, and why is its bandwidth actually defined as it is, and what is limiting its bandwidth. So as you can see from this image, just in terms of the construction, you have two types of waveguides, a rectangular waveguide or a cylindrical waveguide, and or a circular waveguide. And to create the horn antenna, it's just actually an extension of this waveguide up into a larger aperture. So in terms of its assembly, it is rather simplistic in design. Of course, there's some design techniques that you have to take into account to make sure that you actually do radiate properly and match properly with free space impedance. And if you look at these waveguides, so these are these sections at the back here. That's our rectangular waveguide, and that is our circular waveguide at the back. These waveguides can support an extremely large amount of modes. So these can be transverse electric modes, so that the electric field is transverse to the direction of propagation, but you also get transverse magnetic modes where the magnetic field is transverse to the direction of propagation. And typically we want to use these antennas, especially the pyramidal horn antenna and the conical horn antenna, with only one mode dominant. And for the pyramidal horn antenna, that is this TE11 mode. And for the circular or the conical horn antenna, I apologize, it's a TE10 mode for the rectangular waveguide and the TE11 mode for the circular waveguide. So let's just quickly have a look at this. What do I mean with only one mode? For those of you that have not actually looked at waveguides before. Let's first consider the rectangular waveguide. And as I've just shown that you have this TE10 mode. And if you look at the electric field distribution, we know from electromagnetics that tangential electric field on a conducting surface has to reduce to zero. So there's always a zero at the edges of the waveguide. And in this case, for the TE11 mode, it's a maximum in the center. So if we were to plot the electric field distribution on the aperture or within a waveguide, a rectangular waveguide, this is the TE10 mode. Now, as I said, there can be additional modes, and let's just have a look at two of these. Okay, they can also work. So in addition to the TE10 mode, you can also have, for example, a TE20 mode. And in this case, oh, that goes wrong. We have two maxima. So again, we have a 0 We have a maximum in the center. We actually have a 0 in the center and another maxima. I know my drawings don't do it justice, but I hope you can still follow what I mean here. And yeah, for example, you guessed it, there can also exist a TE30 mode. Well, that should actually be in the center. With again, maxima. I believe I did something wrong here. Apologize for that. And that is the phase reverses. So similarly here, phase reverses again, and once again, reverses. And this will be your TE30 mode. Okay, now the reason I show you this will hopefully become apparent a little bit later, but this is just the fundamental nature of the waveguide. Given its shape, depending on what the width and the length of this, or the height of this waveguide is, these modes can propagate at various frequencies. So if we change these dimensions, the frequencies of these modes change. So at a certain frequency, especially at the lower end, the TE1 mode, 10 mode, stops propagating. That's just defined by the dimensions of this waveguide. Similarly, the TE20 mode also stops propagating, but also it means that at a certain frequency, it is actually excited, or it can propagate within your waveguide. And it is this nature of the modes, either the cutoff frequencies of the modes or the modes being excited, that define the bandwidth of your horn antenna. As I said, the mode that we want in a pyramidal horn antenna is this TE10 mode. So the lowest operating frequency of the horn antenna is defined by the cutoff frequency of this mode, and its upper end of this frequency band is due to the excitation of the TE of the higher order modes, not in this case specifically TE20, but it could be other modes as well that will interfere with this electric field pattern that you have at the end of the aperture. Because ultimately, the resulting electric field pattern is a superposition of all these modes. And you want to ideally only have your fundamental mode, this TE10 mode, in your aperture for a pyramidal horn antenna. And exactly the same thing applies for the circular waveguide. So in the circular waveguide, for example, we have our TE11 mode, and this curves a little bit. That should be a very straight line, but I hope you get the idea of it. This is the TE11, but similarly, you can get a TE21 mode as well. And in this case, you have a completely different field pattern. Oh, that should go the other way. So you can see that if this is the mode that you want, and you get this field pattern, then yeah, this will not be, this will definitely influence this field pattern negatively, and you get a completely different radiation. And yeah, the main point for you to remember is that it's these fundamental modes that we want in terms of the performance for a rectangular and a pyramidal, sorry, and a conical horn antenna. So let's just quickly look at some of the dimensions and the influences these dimensions have. You want to extend your rectangular waveguide to a certain aperture width. Now, you recall from yesterday that there was this relationship between the gain and the effective area of an antenna. So maybe I'll write this on the side again, it's easier. You may recall that the effective area is equal to lambda squared divided by 4 pi multiplied by the gain of the antenna. But we also know that the effective area is actually equal to the aperture efficiency multiplied by the physical area of the antenna. So in a sense, if you were to have a high aperture efficiency, increasing the physical area of your antenna increases the gain of your antenna. I hope you can also understand from the definition of gain and directivity that what do you think happens to your beam width of your antenna if you increase the gain or the directivity? So with the beam width, I mean the 3 dB beam width of the main lobe. If you increase the directivity or the gain, what happens to that 3 dB beam width? Does it increase or decrease? Anyone want to take a guess in the chat? Yeah, Miroslav says decrease, decrease, decrease. Great, yeah. So because that's all point with directivity is, remember it's with reference to an isotropic radiator. And the only way that you can increase it is by taking power somewhere else. So you have to have a narrowing beam if you increase your directivity or gain. So if an increase in your area results in an increase in your gain, it's also intuitive that an increase in your area creates a decrease in your beam pattern or in your beam width as well. And that in a nutshell is the design aspects of a pyramidal horn antenna. So you can see you can increase the gain by either increasing the aperture dimension, so the height of your aperture or the width of your aperture of your antenna. And of course, you can increase and decrease your E and H plane half power beam widths inversely proportional to that. So increasing the height will cause a decrease in your E-plane pattern. So remember, the E-plane pattern is the plane containing your electric field. And we just said that the electric field distribution is directed along this, like this, along the aperture. So this will be our E-plane. And if I increase this dimension HA, I'm actually decreasing the beam width because I'm increasing my gain along that direction. Did you clear that? So I want you to quickly have a go at this. This is the design dimensions of a standard gain horn for X-band from 8 to 12 gigahertz. So this horn antenna, if I were to give this in person, I would have had this antenna here with you and you would have been able to look at it. It's your standard antenna that you use in an anechoic chamber for some measurements. And this is the dimensions. So a width of 110 millimeter and a height of 79 millimeter. So I want you to solve the gain of this antenna at 10 gigahertz. If you can have a look on Mentimeter, you can type your answer in there. Stefan, I will try to keep the answer to give you your time still for it. So as I say, Just give me a second. I hope I don't think it has started. Has it started? Let me just quickly start this again before it shows you the answer. That will be terrible. Yeah. So give your answer you've got 5 minutes in decibels, dBi, and round it to 1 decimal point. For those of you that don't have it at hand. And I will say let the aperture efficiency equal 100%. So, oh, I say it there, assume 100%. Danny, you've switched your camera on by accident. Thanks. So we have 9 answers coming in so far. We just wait for the time. Okay, let's see what you said. So the correct answer is 20.8 dBi, and it seems like, yeah, quite a few of you got that. Quickly look at this. .8 dBi. Clear my annotations. So indeed, I think maybe someone gave it in millimeters, not quite. Okay, but I see some people still had some difficulty with it, especially I don't know where the negatives comes from. Yeah, let's just quickly have a look at that. We have the physical area, first of all, is the 110, so it's 0.11 multiplied by the 8 centimeters, which is 0.079 meters. That's our physical area. And we know that the effective area is related like this to the gain. So we know that this is equal to lambda squared over 4 pi multiplied by the gain. What we want to solve is the gain. So we have 0.11 multiplied by 0.079. It should all be in meters, divided by lambda squared multiplied by 4 pi. And this should give you a gain. But of course, this is then in linear scale. So I'm just going to denote this as a small l for linear scale. And if we want to go to decibels, then the gain in decibels is equal to 10 log of the gain in linear scale. And this should get you to 20.8 dBi if you want to try that later on again. Let's see what 10 omega says. So we've asked to design an X-band standard gain horn. If you look at the dimensions, we said the width is 110 and the height 79 millimeters. If you look at the gain at 10 gigahertz, it shows a gain of 9. Oh, am I right? No, where are we? 10 gigahertz. I do not show it here, but that is around 19.4 dBi. So we're not quite at the 20.8, around a decibel less. But remember, we assumed an aperture efficiency of 1. So we don't actually have a aperture efficiency of 100%. And the reason for this, if you were to look at the profile of a horn antenna, just from the side, what you want to achieve is to achieve 100% aperture efficiency is to have an electric field that is perfectly in phase at the aperture. But given the length of the horn antenna, it always results that there's some type of curvature. This is extreme exaggeration of your electric field at the aperture. So what you have in the end is a phase distribution, or not an equal phase distribution along the aperture. And this results in a slightly lower aperture efficiency. So this is the one dimension also that you need to take into consideration, is the length should be such that the phase distribution along the aperture is as constant as possible. And this is why you notice, okay, there's a slightly lower gain than what you calculated. If we were to look at the radiation patterns, so we see here the E-plane and H-plane radiation patterns, and you notice it's got almost similar beam widths, half-power beam widths, but the side lobe level differs quite a bit. So for the E-plane, that's this plane containing the electric field right through the center, we have a side lobe level of around minus 13 dB from the maximum. But in the H-plane, it's quite lower. Now, to understand this, I have to take a quick side tour again to some signal processing. For those of you that have worked with this before, if you were to look at the Fourier transform of a block wave, then what you get in the Fourier domain is a sinc function. And if you were to look at the side lobe level of a sinc function, you get a minus 13 dB level. So for aperture antennas, the way that we compute the far field is by taking a Fourier transform of the near field distribution. So this is in a way almost the best explanation for you to tell you why where this 13 dB side lobe level comes from. And that's due to the fact that if you were to draw the magnitude of the electric field around, if you were to take it along this line here, let's assume this is 0, and at this point here, it's a maximum. As you approach the waveguide, you can assume that the fields are 0. And down the center, it becomes a maximum as a step function, and then you move away again. So you get this aperture field distribution of a block wave in the E-plane. And this is your near field distribution. In the far field, you get this sinc function with this 13 dB side lobe level. If you were to look in the H-plane, so this is the orthogonal plane to the E-plane, the aperture field distribution is more a truncated cosine. So it's again 0 outside of the waveguide. Then it starts at 0, takes a sinusoidal form, and then again goes to 0. And if you look at the Fourier transform of such a function, you'll notice that you get significantly lower levels of side lobe. And this is primarily the explanation for the differences. It's purely due to the fact that the aperture fields are different. And that's why what you see back here. So Mohammed, get back to your question where you said, okay, but how do I now design my antenna for a certain amount of gain in a particular direction? In aperture antennas, this is what you need to be careful for, is what is the near field distribution that you are exciting? And especially trying to avoid the higher order modes. Let's just quickly have a look at how we excite these antennas then. I think in the initial video that we showed, if you had paid good attention, you would have seen this in the video. So now we have a waveguide with a certain wave field distribution, but how do I tap into the waveguide? How do I get a signal onto the waveguide? That's the other question now. And for that, we use this, again, coaxial probe, but in a slightly different way. And now you're familiar with the coaxial cable. But this you should see as the back end of the waveguide. It's actually short-circuited. So if you look at the model, this doesn't contain the antenna. This is now just connected to the antenna. You see at the back, it's a back short. And you should now imagine that your horn antenna is connected to this side here. And what we want to achieve is in this plane here, a field distribution that is the TE11 mode. And the way that we can couple into that is by using this type of probe. So we have a coaxial line and we extend the center probe up into the waveguide. And if you do this properly, you can couple into your fundamental mode. So here you should imagine, again, the fields. Can I copy this one? So the fields extending downwards towards the ground reference plane here, and ultimately coupling into your fundamental mode. So if this is positioned perfectly in the center, you can couple into your TE11 mode that you wanted to excite in the aperture. Of course, at a higher frequency, this probe does not know that your TE31 mode is also possible within this waveguide. So you can also, with this probe, couple nicely into the center of your TE31 mode. And this again limits the bandwidth of this antenna. So this is always something to take into account when you're working with aperture antennas, is to ensure that the method with which it's TE10. Thank you very much for correcting me. Too many ones, so I apologize for that. So TE10 and TE30, of course. Well, that should be a 3. You can notice it's nearing the end of the lecture. So it's the 10 and 30 mode. Right at the end, so this is our last exercise for the day. The conical horn design. There's actually this very nice graph that you can use to look at how you design one of these, the conical horn. Only 2 dimensions. You have the length and the diameter. And if you look at this graph here, you see that the diameter of the horn has this dependence with is related. Let's start that again. The directivity that you can achieve with this conical horn antenna has this relationship between the diameter and the length. So each of these curves here is for a certain length. That's shown here. This is your length L, and that's another length L. And the directivity you can achieve for a certain diameter in terms of wavelength is shown here. So you see that for each length L, you can achieve a peak directivity for a certain diameter. So before that, let's say that maximum diameter, you just don't have the physical area to achieve more directivity. So here you are actually still related to lambda 4 pi divided by lambda squared. This is the relationship here. But after a certain diameter, if your antenna becomes too large, you see this drop in directivity. And that drop is due to this spherical nature of the fields. If your diameter becomes too large, then you start to have a phase variation across your aperture, and this then decreases your directivity that you can achieve. So just again, this graph shows you that for every length, so each one of these curves is a length, and this is the correct diameter to achieve your best directivity. So I wanted to give it a quick thought and look in Mentimeter. I've got this graph again for you, and I ask you to design the diameter for a horn antenna, a conical horn antenna, to achieve a certain directivity. So 2 people have answered. 3. Okay, now the answers are coming. So just again, for those, that the curve that you're looking at for length is each one of these curves is for a certain length. And you want the maximum directivity for a given diameter. I'll wait for one more, then we have 10 answers. There we go. 11 even. Okay, so the correct one is 0.6. So if you were able to figure that one out, there was no need to compute the wavelength, anything like that. It's already on the graph for you. So that's the power of a graph like this, actually. It's quite handy to have at hand. So the curve that we wanted was for one wavelength, and this is this curve here. And the peak directivity you see corresponds to a diameter of 2 lambda. So of course, let's just quickly verify this in Antenna Magus. So we've asked for a gain of 1 gigahertz, a frequency of 1 gigahertz. The gain is around 13.2 dBi. And if you look at the dimensions solved, the diameter, this df, is around 600 millimeters or 0.6 meters. Now you may notice here that this length LF is only 21 centimeters, so not quite the 30 centimeters it should be, but also pay attention that the length here is taken from this edge, and in this design, it's taken from this virtual peak of your conical section. And here you have to trust me, but I calculated this quickly, and that extra distance is approximately 10 centimeters. So it does indeed line up very nicely with that graph. In the last minute, I'm quickly going to run past this. It's now just a bit at the end that I'm just throwing at you, but I'd like to also end in time. The one thing that you should notice here is if you look at this field distribution for the conical horn antenna, you see that there's this curvature in the aperture field. And this, of course, can be decomposed into 2 field components. So one inherent problem with a conical horn antenna is it has this inherent cross polarization that it has. So of course, if you are trying to transmit in a vertical polarization, you will have some cross polarization in some angles. And that is just due to the physical properties of the aperture field distribution. There's a very nice way that we can get away with that, and you've probably seen this in some horn antennas, and that is to create these corrugations. So in a corrugated horn antenna, they place these corrugations, and the idea is that this short circuit at the back is transformed to an open circuit in a particular frequency range. And this results in the fields actually being confined to the center. So you no longer actually have a maximum anymore in the center, but you also don't have any cross-polar field component. So you can maybe see this better in the conical horn antenna example that I will show next. If you look at the circular waveguide, we've got this curved electric field at the input, and then you've got these corrugations along the horn. So this means that these field components that are propagating near the edges of the horn, especially the ones that are normal to that direction, are actually completely suppressed. And you only have a vertically oriented field that is transmitted by this horn antenna. And your fields are mostly contained in the center of the horn antenna as well, since the normal components are again suppressed. That's just a little side note on horn antennas. you will come across these corrugations, and that is to suppress your orthogonal field component, so cross polarization, and also to create a more symmetrical beam pattern, because here you've got a symmetrical near field, which translates in a symmetrical radiation pattern as well. We did not even touch reflector antennas yet. So I think I will leave this to start with tomorrow. And then tomorrow we'll jump straight into antenna arrays. Now, for those of you that have been present, I mentioned that I will try a software demonstration. But I had also been a little bit ambitious with how fast I'll go through the material. So antenna arrays are by far the more important. So of course, by tomorrow, I mean on Friday. Thank you. There's all the same days for me. So on Friday, I will have a look at antenna arrays. And then we'll actually do a quick, we'll end the course then with an architecture design for an aperture array that could potentially create 2 beams in the sky simultaneously. So I look forward to seeing you on Friday. I'll be sending you the notes probably tomorrow for the material we handled today. So thanks for the participation.
Thank you.
You're welcome. Thanks.
Thanks, David.